All right, so this is section 15.5, part B. This will be a 2-video lesson. It's going to be a little strange here because the first lesson is going to be much shorter than the second lesson. First one's only going to cover these first couple of pages here. Then the last one's going to be about 25, 26 minutes. Actually, there's actually a part C and a part D to this particular section. Section 15.5, we are not going to cover those right now. If we have time, at the end of the year, maybe we'll come back to it, but most likely we are not going to get to part C and part D. Okay, but part B, we are definitely going to get to. So we're still going to be talking about applications of double integrals. We're going to be talking about computing mass, and this one we're going to talk about electric charge, and then center of mass, which we've done in moments of inertia. So, same idea that we had in 16.5a, but this time we're going to have variable density. So in 16.5a, we had a constant density. In this case, we're going to talk about things which have variable density. So what's the idea behind that? Well, this is going to be a horrible drawing, but for lack of a better space here, this is some kind of a field that we've got. Maybe it's an actual like field on the ground or whatever. So we'll say that this is some kind of a field. And in this field, we've got a certain number of ants. We've got a certain number of ants in a field. What we're going to have is we're going to have a certain density based upon the location in the field. So we are going to basically still say that this is like an XY coordinate plane. We're going to label the field like it's in an XY coordinate plane. We're going to have a certain density of the amount of ants in the field. So really what the density is going to be is the number of ants per square foot. That's an S. Per square foot. So for example, let's say that this point right here represents the point 2,2. So we're actually going to have some kind of a point associated with 2,2. Okay, that specific point, if we look at that one place, we could actually figure out what the density is just by looking at that one point. So we're going to say that, and I'm just giving you this because I don't know what it would actually be here. We're going to say that rho of 2,2 is 7. So we're saying that we've got a density of 7 ants per square foot at that 1.22. But what if I want to use, or what if I want to try and figure out the density of the entire field? Well, to do that, and this idea is really nothing that we haven't done before, to do that, what we're going to do is we're going to partition off this field in different segments, and equal segments, the best that we can. But we're also going to have to partition it off horizontally as well. Something like that, and then maybe you've got another section up there at the top or something, so that all those rectangular spaces are relatively equal. Well, it just so happened that I didn't really draw this on purpose like that, but that point that's in the middle there is kind of right in the middle of that box. Doesn't have to be. It could be in a corner. It could be in the upper center or something like that. The point does not have to be right in the center of the box, but we're going to use that point to estimate the density of that particular box. So that box region. So in order for us to actually get that, we're going to have to label what our partitions are here. So maybe each one of these green lines, maybe like this one goes from 1.7 to 2.3, and we'll just say the same thing on the other side just for ease of it. So each box basically is a 0.6 by 0.6 box. And then obviously, if we wanted to estimate the entire field, what we would do is we would take a point someplace within each one of these boxes and pick a known density, or figure out what the density is at that one point, and use that density to estimate, okay, that's going to be the density of that entire box. The smaller and smaller we can make those boxes, the more accurate our density for the entire field is going to be. In this case, we're going to say, okay, so what is the actual density of that box? Well, let's see. We know it's 7 because that's the actual density at that one point of 2,2. So we have 7 ants per square foot. And then we're going to multiply that by, what did I say? It's going to be 0.6 times 0.6, so 0.36 square feet. I'll just write it as feet squared. If you were to multiply these two things together, the ants per square foot times the 0.36 square feet, the square feet are going to cancel out, and all you're going to be left with is the total number of ants, and 7 times 0.36 is 2.52 ants. So what we would actually get there is the total number of ants by using the density and multiplying it by the area. And hopefully that kind of rings a bell, because what is the density multiplied by the area? Density multiplied by the area in 2 dimensions is the mass. So let's go ahead and write that. So remember that if we take a double integral, and that's exactly what we're doing, by the way, because we've got a change in the x direction and a change in the y direction, and we add up all of the boxes left to right, all of the columns up top to bottom, or vice versa. We add up all of the row xy dA, you end up with the total mass. So we'll get the total mass of the ants in that field, I guess. All right, so let's go ahead and look at one where we're actually dealing with some physics here. We're going to deal with some electrical charge. So our first example, charge is distributed over the triangular region D in figure 3, so that the charge density at xy at any point is, and then you've got your, I believe that is a lowercase omega, which is the symbol for charge, electrical charge. So your charge at any point xy is defined to be the product of x and y, which is measured in coulombs per square meter. So it's a capital C per meter squared. Find the total charge. All right, so what we can do is we can look at this, and we don't really have to do this next part, but I think it's a good idea just so you see what's happening here. At this particular point, that's the point 0, 1. If I were to plug that into this equation, 0 times 1, it's going to give me 0. So my charge is 0. 0 coulombs per square meter, right there at that particular point. Likewise, if I were to look at this corner, that's the point 1, 0. Well, once again, because if I take 1 and 0, multiply them, I get 0, so the charge is 0. And then if I were to look at this point up here, we actually get some charge here. So I'm going to plug in 1, 1, and my charge is 1. And then if I were to look at some point like right in the middle, we'll call this like 1/2, 1/2. The charge there, half times a half is a fourth, so we would get a charge of 1/4. Well, what we're looking for here is we're looking for the total charge over that entire lamina, over that entire field that's given by that triangular region. So we need to find total charge. Obviously, we could take and add up every single possible charge, but that's going to be a little bit challenging to do. So the total charge, instead of taking every single possible point, because you can't really do it, you can take integrals. Total charge is going to be a double integral of our density function, which was given as xy, and then we have to do this over our area. Yeah, over D. So our double integral over our domain of xy dA. Well, so now we have to figure this out. And the arrow up there indicates that we should do this as a type 1. It doesn't really matter. We could do it as a type 2. Probably easier to do it as a type 1 because it's already solved for y equals 1 minus x as far as this particular function is concerned. So I think type 1 here would be the easiest. Okay, and remember type 1 is dy dx. So the y has to be the inside part. So y is going to vary from this function, because that's the bottom one, all the way up to, let me extend the screen, this function, which is the top one. So here's your arrow that they already had in there for us. Let's make that an arrow. So we're going to vary from 1 minus x up to 1. And then the x values are going to go from a number to a number. So x varies from 0 to 1. Okay, it goes from 0 to 1. And then from here, it's just literally about doing the antiderivatives and finding the total value here. So let's go ahead and do this. So the first antiderivative will be with respect to y. So we're going to get 1/2 xy squared evaluated from 1 minus x to 1. Don't forget we still got to do dx at the end. So let's see, plugging in a 1 for the y gives us 1/2 x. Plugging in the 1 minus x is going to give us 1/2 x times 1 minus x squared dx integral 0 to 1. All right, technically I can pull the 1/2 out to the front. Let's do that. And then we're going to get, well, actually, let's see, we're going to get x minus, going to have to do a little bit of foiling here. So if I FOIL that, it's going to be x times, let's see, 1 minus 2x plus x squared. Distribute the x. So we're going to get x plus 2x squared minus x cubed dx. The nice thing is the x minus x go away. So I'm left with taking an integral. Oops, forgot my bounds. From 0 to 1 of 2x squared minus x cubed dx. All right, so let's see, what is that going to give us? 2/3 x cubed minus 1/4 x to the 4th. Don't forget the 1/2. Evaluating that from 0 to 1 is going to be 1/2 times. Plugging in a 1, we're going to get 2/3 minus 1/4. Plugging in 0 goes away. So it looks like that's going to be, I'm going to distribute the half. You can do this in any order you want to. I'm going to get 1/3 minus 1/8. So that's going to be in terms of 24ths. So it should be 8/24 minus 3/24 is going to give us 5/24. That is your charge. Now there is an interesting thing about this, and I'm actually doing a little assuming here, but the fact that it's 5/24, 5/24 is definitely less than 1. It's definitely less than 1/2. If you go all the way back up here, at this corner we had a charge of 1. Right here we had a charge of 1/2. If I'm kind of adding up all of these different charges over this entire thing, and the fact that these two, I'm sorry, was a charge of 1/4. I've already got 1 and 1/4 at just those 2 points, but the overall charge is 5 over 24, tells me that we must have some negative charge in there to counterbalance this. Again, I could be wrong about that, but it seems to be logical. So again, anybody who's in physics maybe can help correct that if that's not the case, but I do believe that's the case. All right, so this is really the end of video 1. The second video will be about 25 minutes, and it will pick up on the next page.